So, yeah, this is the problem 50 was the problem that was chosen, and this problem won by literally one vote. I'm not kidding. One vote is how much this one won by. So, all right, let's do it. So, problem 50 says a particle of mass 0.5 kilograms moves along the x-axis with a potential energy whose dependence on x is shown below. What is the force on the particle at x equals these three things? In fact, let's separate them out so they're not so bad, like that. So yeah, we're trying to find out what's the force on the particle there. Let's just start with that. So in order to get the force, well, I got to go to that idea that the force using a potential energy graph is equal to the negative derivative of potential energy with respect to x. So, and that's the negative there. I'm not going to go too much into the negative explanation, but if you're confused about that, go back to when we were first defining the defining conservative forces and how they relate to potential energy. Basically, it comes from this relationship: the work done by a conservative force is equal to the negative change in potential energy. Anyway, though, so I'll use this. So basically, I need to take the derivative at any one of these points in order to find this. And the derivative, again, if you've got these, look at this. These are all straight lines. So I don't even need to, because I don't know what this function, what this equation looks like for this graph. In fact, it looks like a bunch of pieces, actually. But I can, what's nice is this graph is just, a bunch of straight lines. So where the derivative is just essentially going to be the slope. Right? The derivative is actually the instantaneous slope at any moment, but if it's a straight line, it'll just be the slope of that particular line. So, all right, let's look at that. Let's make this a little bit bigger here. So let's see, at x equals 2 on this graph is right here, and what's the slope, right? What's the slope of this graph? The slope of this graph is just 0. So the force at x equals 2, so let's say I'll make a little diagram here. So the force so this is the force as a function of x, right? So the force at 2 would equal 0. Yeah. So the force then at 5 meters, that's going to be here. Wait, nope, that's 6. Sorry, I'm about to say, you can't find the slope of that. So the slope of here, 5, boom, we're going to go up here, trying to find this slope. So let's pick 2 points that are easy to find here. I would say easy points are here and here. So this point up here is going to be, looks like 6 meters, 12 joules. And then easy slope down here would be 4 meters, 4 joules. All right, so, and then if I find the slope of that, so the slope of this is going to be, slope would be 12 minus 4 divided by 6 minus 4. So it's going to be 12 minus 4 is 8. 6 minus 4 is 2. So this is going to be 4. But again, remember, this is the slope. So this is du dx. But we want the negative slope. So that's going to be negative 4. What is it? Newtons, right? Because it's a force. So this is going to be equal to negative 4 newtons. So this is the force then at 8 meters. That's the next one here. So at 8 meters is here. Again, I'm trying to find the slope of this line then. So I'm just going to use this actual data point right here. So I'm going to use the same data point here, but then I'm going to use this data point here because this is going to be really nice and easy for me. It's 8, 0 joule, 8 meters, 0 joules. That's that data point. So then I'm going to find this slope. And that's going to equal, let's see, 0 minus 12 divided by 8 minus 6. So that's going to be negative 12 over negative 12 over positive 2. So that's going to be negative 6. But again, this is the derivative. I want the negative derivative to get the force, because again, force is the negative derivative there, so it's going to be 6 newtons. So that's going over here, 6 newtons. And then lastly is 12 meters. So at 12 meters, let's use this. At 12 meters, that's just going to be right here, and the slope of a horizontal line is just going to be 0. So again, I get 0 there. And so here's all for A, part A. Okay, for part B then, part B says if the total mechanical energy of the particle is -6 joules, let's get rid of that. So the total energy is -6 joules. What are the minimum and maximum positions of the particle? Okay, so I think I'm going to copy this and paste it down here just so I got a clean thing here. So they're saying that the total energy, so the total energy is -6 joules. Well, what that -6 is down here, right? And now what I'm going to do, and hopefully this is going to make a little sense to you, is that I'm going to first make dotted lines here. I'm going to make a solid line here, and then dotted lines here. Why would I do that? Well, so what I'm going to show you now is this Fet simulation, back to this Fet simulation. So you can think of these curves, these paths right here, just like the graph. Let's use my mouse here. You can probably see that a little better. So you can think of these curves as just like the graph, right? This is like the potential energies I can have here, right? I could have a potential energy of this big, and then the skater, she's going to oscillate back and forth between between those things, and then that's like the most potential energy I could have. But so that's like giving like that much energy. It goes that much potential and back and forth and back and forth. Or I could redo this, and I'll put her just this far away, and now you can see she can't go any higher than this point, right? So her total, if I were to do the total energy of the graph, look at the total energy, it's not changing. It would just be a horizontal line, and that energy gets transferred between kinetic and potential and kinetic and potential. Let's look at something more complex. What about something like this? Here's the types of potential, the amount of potential energy you can have, and then the position is along the horizontal right there. But so for example, if I set her down here, well then you got a small amount of energy, so she can really just oscillate in this well, this potential energy well right here. It's just going to go back and forth. She's not going to be able to go into this area right here because there's too much energy required to make it over here. So really, she's just going to oscillate back and forth like that. Where if I go up here, well now she has enough energy to go up over this hump and make it around here, right? So the total energy of this system is all around here like that. And she can just keep oscillating back and forth and back and forth. The energy changes between potential and potential and kinetic, but the total energy stays constant. So why do I use that? Because this is pretty much a similar idea here. You can think of like the track up here. What they're saying is that -6 joules, that's the total energy I have to work with. So basically, what I got in what color is it? Yellow? What I got in yellow here is a constant, right? Because it's just -6 joules right there. In fact, let's make this yellow as well. So there we go. So it's -6 joules there, but this is the potential. While the potential energy of the graph, these are the potential energies that could occur should you have enough energy. We don't have enough energy. We have -6 joules. So she would never, if she was like skateboarding, she'd only be able to oscillate back and forth between these two things, never be able to get up to these high potential energies. It's just not going to happen. You need more energy to make it up to those potential energy points. So that's why we make a dotted line here, is we're saying while the energy is -6 joules, none of this is going to apply. The particle, or whatever you want to say, is in this potential energy graph, is not going to be able to reach here. It's only able to reach here. So that's kind of the idea of what we're doing. Okay, so they're saying it's that. What are the minimum and maximum positions of the particle? Well, this is a potential energy versus position graph. So if your skater, your particle, is only able to go from here to here, right, then the position, the maximum positions would be, you can extrapolate here, right? I'm going to try and read off this graph here. So let's see, this would be a graph of 10 meters. This would be 10 meters here. So this must be 9 meters, right? So 9 meters would be the minimum position. And then here's the maximum position is here. That's just below 16 but bigger than 14. That looks like 15 meters to me. So this would be the maximum position right there. So, and that's basically what we're doing. We're basically saying with this, with this position graph, what's the biggest it could be and the smallest it could be right there. I think that's all they're asking, right? Yeah. So then what are these positions if the total energy is 2 joules? Again, let's just paste it again right there, right? So now we're saying that the total energy is positive 2 joules. Right? Well, positive 2 joules is right here. Still not enough to again, let's keep it the colors consistent. Sorry, had to restart. There we go. So positive 2 joules would be here. This would be positive 2 joules. And again, not enough energy to make it up here. But then I would have enough energy here, and then again, not enough energy to make it outside there. So basically, again, she'd be if I placed her with this much energy, I started her here, she would oscillate back and forth. The skater or the particle or whatever would oscillate back and forth along those potential energy graphs. Here, the skater or the particle would have maximum potential energy. I'm sorry, maximum kinetic energy, because that's the lowest potential energy. And then this is where you have the most potential energy given that thing. So what? Oh yeah, we're trying to find out the minimum and maximum again. So I would say about right here, right? About right here is the biggest that you're going to get there, and then about right here is the biggest that you're going to get there. So I would say it's a little less than 17. It looks like, but bigger than 16. So let's say 16.5 meters is the maximum position here, and then this would be 7.5 meters would be the minimum position. So then finally we're looking at if the energy is 16 joules. So now if the total energy is 16 joules, what speeds of the particle at the positions in part A? What are the speeds of the particle for these positions in part A? So now we're trying to look at the speeds. So okay, let's do that now. So I think again I'm just gonna copy and paste here just to get a clean chart here. So all right, and the speeds again, the positions are so say x1, x2, x3, and x4. We got the total energy is 16 joules, and then 2, 5, 8, and 12. So total energy is 16 joules. So that's way up here, right? Or I guess it's not that far. It's maybe up here. But 2, 5, 8, and 12. So 2 meters, 5 meters, 8 meters, 12 meters. So what I'm going to do now is use the fact that so we'll start first with x1 is 2 meters. We'll start here. And then I'm going to use the fact that the total energy, maybe I'll throw it over here. So the total energy is equal to the potential energy plus the kinetic energy. So the total energy they told me was 16 joules. What's the potential energy then at 2 meters? Because again, this is a potential energy versus position graph. Well, the potential energy at 2 meters is 4 joules. So this is 4 joules plus the kinetic energy. So the kinetic energy then is 12 joules. But they want the speed, right? Well, luckily, kinetic energy is 1/2 mv squared. So this is going to be 2 times 12, and they told me the mass was 0.5. So if I take the square root of that, I don't know why I got this at such an angle. So this is going to be 2 times 12 divided by the mass, which is 0.5, because they told me the mass of the particle is 0.5 back in the beginning of the problem. So say that mass is 0.5 kilograms. And then this will be, so I'll take the square root of all this, and that'll be, so what's that? 24 divided by 0.5. Take the square root and I get 6.9. So let's say 6.9 meters per second. That's how fast that's going there. So let's do it again for position 2, which is 5 meters, I think. Yeah, 5 meters. So total energy again. So I'm using this same relationship. Total energy is kinetic plus potential, or potential plus kinetic. Total energy in this case is still 16 joules, but the potential energy now at 5 meters is, I'm going to say 8 joules. I'm going to say 8 joules. So kinetic energy plus 8 joules, that means that the kinetic energy is equal to 8 joules. But again, they want the speed, so 8 equals then the equation for kinetic energy, 1/2 mv squared. So it's going to be 2 times 8 divided by 0.5. Take the square root. That's going to be my speed. So that's 16 divided by 0.5, so times 2. Square root of that is 5.7 meters per second. So that's for that one. Let's keep going here. Just move off over to this side. Next up is 8. At 8, right, at 8, the potential energy is equal to 0, right? So at 8, the potential energy is equal to 0. So let's do this. So we got, again, this is x3 equals 8 meters. So total energy is the kinetic plus the potential energy. Potential energy, though, I just found out was 0. So that means then 16 joules is what the kinetic energy is equal to. Again, we want the speed, though, so it's going to be 1/2 times the mass times the speed squared. So this is going to be 2 times 16 divided by 0.5 square root. That's the speed. So it's going to be 32 divided by 0.5 square root. So that's 8 meters per second for that one. Last one, which is position 4, which is 12 meters. Again, total energy is going to be the kinetic energy plus the potential energy. Total energy is 16. What's the potential energy at 12 joules? The potential energy, or sorry, at 12 meters, is equal to, it looks like 12 joules. It looks like 12 joules. So down there, that's the potential energy. Oh, sorry, negative 12 joules. Negative 12 joules. Careful, careful, careful. So this is going to be kinetic energy plus negative 12 joules. So this is going to be then, the kinetic energy will be 16 plus 12. Why do I need a calculator to do that? That's so pathetic. So we get this. And again, we want the speed, though. So we're going to do 1/2 mv squared. 2 times 28 divided by 0.5. Take the square root. 0.5. So that's going to be divided by 0.5. Square root of my answer. I'm getting 10.6 meters per second. And that's the velocity there. And there you go. There's that one. So, yeah. Hopefully that helped. All right. See you later. Bye.